right, so we got that. Okay, first thing first, are there any questions about the homework assignment? Hopefully this time is a little bit better. Yes? Okay. All right, so I think we can finally get to assembly language programming. In the past, I start with assembly language programming, which is, the next thing that we're going to talk about. And you might think, well, that will give that means we have the entire semester to talk about assembly language programming, so that has got to be the better way to do things. Well, unfortunately, that is not the case, because when I do explain assembly language programming without first talking about the architecture, most people do not understand, what is going on with the individual instructions. So it's only by trial and error that some people start to figure out, oh, so this is doing this, oh, so that is doing that. So in this class, starting with this semester, I'm doing, well, I started a few semesters ago, but this semester I'm particularly using this approach of bottom-up approach, okay? So we first start with, remember, transistors? So we are now building from transistors up to the processor, and finally instructions, because the instructions are now implemented by microcode stuff that is orchestrating everything that's going on inside the processor. So by doing that, now we can actually get to the actual instructions. But before we get to the actual instructions, we will talk about mnemonics and the assembler, okay? In other words, at this point we have not even introduced the concept of what is a mnemonic and what is the assembler, and which is a great thing, because for those of you who have tried to write a program using the instructions of the toy processor that we have talked about so far, what is the process for of writing a program using those instructions?
Taking an hour to figure out all the bytes.
Okay, and that's because the instructions are only they come in the form of this, right? Okay, so let me just kind of pop up a page first, because at this point the only documentation. Oh, I don't need to log in because this is just read only. Because at this point, this is how we know about the instructions in RAM. Okay, we just know that 0110110 means we are supplying a register A with a value that is right after the opcode itself. Okay. And the next one is 0101101, which is E equals to whatever the value is after the instruction, the opcode itself. If you want to do a branch, how do you do a branch? Okay, a branch is PC equals to X unconditional. So we have to look for that one. Okay, which is right here. Okay, PC equals X, which means we are taking the value of a register and overwrite the program counter with that register. But how should you initialize that register to begin with? Well, that depends on where you're going, right? How do you know where you're going? Well, now you have to count bytes. You have to actually count the locations and say, oh, we have to go back to location 5 because that's the place where the loop begins. Okay. What if you change your program and you say, okay, but there's some more stuff I want to do before location 5, then that shifts everything down a little bit, right? Then you have to go back and go now have to recount all the bytes, right? Because that shifts all the places of all the jumps. So it is doable, it's just not very enjoyable. Okay, the first time you do it, it may be very novel. The second time you do it, it's like, yeah, I know how to do this. The third time you do it, it's like, I don't want to do this anymore. Because there's a lot of detail. Now, did people write programs this way before? Okay, they figure out the bit patterns, they figure out which bit pattern is which instruction, and they manually count the locations for jumps and for variables and stuff like that. The answer is yes, because the first computers did not have an assembler. It's a chicken and egg problem, right? How do you write an assembler prior to having a computer?
How do you make an assembler for an architecture that doesn't exist?
Exactly. So I want to look up the Altair computer. Okay, let me see. This is a good one because I always enjoy popping up this picture. Okay, so this is an Altair computer, and you're looking at the entire computer. There's no USB port in the back of this computer. It's not Bluetooth enabled. Okay? It has no Wi-Fi capability. So it's not like, oh, we're hiding a cordless keyboard and a cordless mouse somewhere. This is the entire computer, short of the actual plug to the power outlet. So how do you program this? What is the user interface of this entire thing?
Switches?
Yeah, toggle switches. They're very tactile. Okay? You're going to go pop, 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 right? That's how you do the input. Where's the output?
The light bulb.
The LEDs. Are we kidding? This is not even that old. It has got LEDs. It's not little light bulbs. These are actual LEDs. So it cannot be that old, okay? Because the things that are even older would have light bulbs. These are all LEDs. They're LED LEDs. Okay. So now the question is, then how do we specify a program? Exactly the same thing that you have to do to write programs for the toy processor that we are currently implementing. Okay, you figure out the bit patterns, you figure out which location. So one part of the switches will control probably the address, okay? So you select the address, and then the other part will select the actual instruction. So you have everything, all the switches in the right position, and then there's one little toggle somewhere and say, right, which is emulating the clock that we have in our processor that would actually program a location in RAM. And then what you do is you specify the next location, and then the next location, and then the next location. And then probably there's a way to switch this whole thing into a quote-unquote run mode. Then you actually start to run the program, and depending on what the program does, the LEDs will light up in a different way. Which is not a very easy way to write programs.
It took a while, didn't it?
Yeah, but people did it. Yes, people did it. It doesn't have that much memory. It's not like you're going to write a 20 megabyte application using this particular method. A program probably typically has hundreds of bytes or something like that. But it's still a chore. Okay? It is still a chore to write several hundreds of bytes or several hundreds of instructions just by toggling switches. Yep.
Those instructions weren't portable from this computer to another computer, though, were they? So
Not
if you wanted to
portable?
program two computers to do the same thing, you had to program both computers to do the same thing.
Well, there's a storage device here. Okay, I'm pretty sure this is a storage device. I'm not really sure whether it's a tape or whether it's a disk. Okay, from the looks of it, it looks like a disk of some kind. So it does have some kind of storage device. So I'm assuming you can actually save the content of RAM into a disk and then put it into another computer. I'm not sure. But the bottom line is, when you need to write instructions and the only thing that describes the instructions is a table like this, it's not very pleasant. Okay, if I just want you to write a subroutine to compare two strings, okay, and say, tell me which string is larger, just using these instructions, it's doable. Okay, we have everything that we need in order to do that, but it's not very easy. Okay, so that's why people came up with the idea of mnemonics. So I'm getting back to my little reminder here. We are supposed to talk about mnemonics. Mnemonics is really, okay, if you look it up on the internet, you look up the definition, it says it's the study and development of systems for improving and assisting the memory. But in the context of assembly language programming, it's really just using something that resembles English words or acronyms in order to say, oh, so that's what the instruction is doing. Is that okay? I'll give you an example. Let me first sign in to my account so I can make changes to the document. So that would be this one. Okay, so let me get back to this document, refresh, so that now I have write access to the document. Okay, so in this particular case, I can call this instruction something like LDI, A, and then a number, okay? So the number is just XYZ, okay? So LDI obviously is not an English word, but it means load immediate. Now, do you have to write it down? No, because this is just something that I just invented. Okay? LDI stands for load immediate. Immediate immediate means whatever the value is right after the opcode is the value that you want to put into the register A in this case. Okay? So load immediate A with XYZ. XYZ is the constant, A specifies the register. The other instruction, okay, let's take a look at this one. This is an easy one. You can just call this add, right? So you can call this add XY. So we are adding the two registers, one is X and one is Y. So if I choose one particular one, okay, so let's take one particular one, which is 100000, say 01, okay? So in this case, XX is register A, right? And Y is register B. So the mnemonics of this particular one can be add AB. But is it easy to remember? When you look at code like this, remember this is one of several hundreds of locations, okay? Versus reading something like this. Oh, I think this is a little bit easier. Okay. We'll pick another one. Okay, so we'll pick this one here. PC equals X. Okay. Now this is an interesting one because historically speaking, there are processors who would do branching like this. Okay, they would change the program counter explicitly using a register. Okay, this is called branch and link. BAL with a register, BALR. Okay, which stands for branch and link with register. That may not be the entire case. Okay, I'll take it back because I think branch and link, has the register serving a different purpose. So, but it is, an instruction. You can say, we are jumping to the location pointed to by the register X. So it is kind of a jump instruction. Okay, just to be consistent, use uppercase. But the mnemonics makes it easier to understand because now you can say, oh, this is a jump instruction. We are going to continue execution where the register X is pointing to. Or I'm adding two registers and storing the result back into A, and so on. So mnemonics really help us remember and be able to understand the program a whole lot easier. It is not easy, but it's a whole lot easier than looking at the binary bit pattern and then be able to and then having to look up a table like this to figure out, oh, I see, 10000001 is adding register A and register B and store the result back into register A. Does that make any sense? Yep.
Is there a limit how long your mnemonics device can be?
Well, the mnemonic is really just a name. Okay, so that when you write your program, you are using the mnemonics. So typically, people use 3 or 4, maybe 5 letters for the mnemonic, and then you will specify something after that as the operands. So this is the actual mnemonic for the opcode, and what is after that is called the operands, which are kind of like parameters. So if you look at the name of the mnemonic as a function name, then these are more or less like parameters. Okay, go ahead.
I was going to say, so it's kind of like a function call basically.
It's kind of like a function call because in some way it is kind of like a function call because you are going to the microcode of the ROM to execute slices of microcode corresponding to that instruction. So in a way, in a very weird way, it is like a subroutine, but it's not exactly like a subroutine because you cannot call inside the call. So it's a one-level call, limited only one level. So are there any questions about the idea of mnemonics in assembly language programming? It's just a name so that we can more easily specify the instructions, that's all. Instead of using a binary bit pattern, which is kind of a hassle to deal with, now you can refer to the mnemonic, which is a name, typically easier to remember.
There's a whole list of names.
And there's a whole list of names too, yes. All right, so are there any questions about mnemonics? No questions? Now, I understand that you guys probably don't have time, but this is a really cool movie to watch since we are mentioning mnemonics. Mnemonics. And then just say Johnny ahead of that. Johnny Mnemonics. It's a movie that's probably, well, I don't know. I mean, Some of you are probably not even born yet when this movie was done. It's an interesting movie. You know, they only gave it like 3 stars out of 5, but it's actually pretty cool in a way. Basically, what's his name? Keno Reef, you know, was a human hard drive for smuggling information. So he would load himself with, you know, information in his head, and his job is to smuggle information to whoever is paying him. And he got sucked into a conspiracy because he was smuggling information to a rebel organization, and then, you know, some nasty things happened. But along the way, it's very interesting. The leader of the rebel is not even human. But I'll let you guys watch the movie to find out, you know, what the leader really was. All right, so mnemonic, that's done. It's a topic that is done. So now we are moving on to the other part. Okay, so with mnemonic, we have to talk about the assembler, because the assembler is basically a really handy tool to help you write programs in assembly language. Because in addition to being able to translate from mnemonic into the binary bit pattern, it can also count byte locations, instruction locations, and you can use symbolic label names. So I can say, okay, this is the label. Okay, let me give you an example of what I mean by using a label and being very helpful by being able to use labels. There we go. So you can have, you know, some instructions here. Okay, so you can have add AB, register A and register B, load immediate, register A with the value of 1. Probably want to do that before. Okay, so we have that. And what you can do is now you can have a label, you know, L1 for instance, and then you can say compare. Okay, so compare register B and register C. Load immediate. Okay, so load immediate register D with L1. And now you can have a conditional branch, right? You know, JZ, and then use register D as a label, or something like that. Okay, you know, this is something you need to do, but you can do something like this, which means, you know, this is L1, which is the label. This is the definition of the label L1. You know, as a colon.
D with L1.
Yeah. So so if you have additional instructions in between, it will still know where L1 is. If you have additional instructions before L1, before the definition of L1, the assembler will automatically count the bytes for you, so that you don't have to do all the counting. I would call that pretty handy, right? Confused about?
The L1 is referring to the, what would you call it, tag that defines that sequence.
Okay, so let's go ahead and just do it like this. Okay, so we'll go ahead and do it like this. So we'll say subtract A from C. Okay, A is loaded with a constant of 1, right? So this is kind of a loop now. Okay, we are loading register D with the label L1, and this can be done before because register D is not getting changed. We are subtracting 1 from C for each iteration. Okay. Okay, so once again, what is the binary code of the subtraction instruction? I cannot remember. I'm not expecting you to remember either. Okay? So if I were to write this program in actual binary code, then this is what the assembler is really doing. Okay, so this is actually a very good example. So the assembler is doing, okay, is doing actually what I'm going to do now. Okay, so the assembler looks at LDI and go like, okay, what is the LDI instruction? The assembler will figure out and say LDI corresponds to load with immediate, which is this instruction here. So the assembler would say, okay, we need this byte 01101100 as the opcode, and what is the constant that we're loading into register A? It's a constant of 1, 00000001. And what is the code to add register B to register A? So that would be, we have that already. Yep, exactly. So the assembler is doing all this stuff for you, okay? But in addition to just translating mnemonics into the binary bit pattern, it can also track labels, okay? So the assembler will now say, okay, we have a label L1 here, okay? So, and it will just make a note, okay? So what the assembler is saying is, oh, L1 now has a location of 3. Assuming this program starts at the very beginning of RAM space, the assembler will now say, oh, L1 is a symbolic name of location 3. Is that okay? So that you don't have to track it. The assembler is doing all the counting and tracking everything. You just have to use the name L1 as a symbolic name. So in the next instruction, when I have something like this, okay, so the instruction or the assembler will now say, oh, we need an LDI with a register D, and LDI is this particular back pattern. D is going to have a 1, 1 at the very end. So we now have the instruction of 0, 1, 1, 0, 1, 1, 1, 1, which is load immediate D with something. What is that something? Ah, it is a reference of L1, and L1 is defined to be a label of 3. So now we can say, oh, it's just 3, which is 0, 0, 0, 0, 0, 0, 1, 1. Then we want to subtract A from C. Okay, where's my subtraction instruction? It's right here, okay? So the byte, or the bits corresponding to that is 1, 0, 0, 1. The XX is C, 1, 1, and then A is 0, 0. And then we have a compare right here.
I think that bit pattern is backwards because X would be A, right?
X would be
C.
C 1 0, not 1
Well, C is 1, 0, but A should be in the X position and C should be in the Y position, right? Or
no, this is correct. The order.
Oh, you're right.
Yeah, this is the right order. And then compare is the same thing, except it is a non-changing subtraction, and that is down right here. 1, 1, 1, 0, and then we have B, which is 0, 1, and then C is 1, 0. And then JZD is jump if and only if the Z flag is set. So that we just implement it in right there. So we have 1, 0, 1, 1, and then the register that is used to supply the location to jump to is D, which is a 1, 1, and then we have the 1, 1, which is a part of the constant. I just did the human assembler thing. Okay? Yep.
So is label kind of being used like a variable here?
No, it's more like just a symbolic name, that is remembering a location.
So all it is a reference to an address in your code.
Yes. So the assembler keeps track of the current location in RAM. So whenever you say a label definition, a label and then a colon, it will just say, oh, so you want this symbolic name to equal to the location right here.
I see.
So later on, you can refer to the symbolic name, and you don't have to do any counting. Question? Okay.
So why is it automatically equals 3? Is it because it's the third?
Because it's location 3. Because
okay. It's
when you look at the locations, yeah. Because at the very beginning, okay, this is at location 0, 0 in hexadecimal, and whoops, I cannot type colon. Okay, and this is at location 2, right? Because 0, 1, and then 2. The label definition does not use up any space because it really is just a operation inside the assembler to make a note of what is this location. Let's call that the symbolic name L1. So now we have location 0, 3 here. Takes up 2 bytes. Location 5 here, and then we have takes up 1 byte. Location 6.
What happened to 1?
It's 0, 0 is the first big bit pattern. 0.
Yeah,
one,
this is location 0, 0, location 1, location 2, 3, 4, 5, 6, location 7. Okay, but the assembler is doing all of this. Okay, that's the job of the assembler. It takes a program represented in mnemonics and labels and convert it into the binary opcode and figure out all the locations so that you don't have to do all that counting yourself. Yep.
So this is von Neumann architecture because everything is in the RAM.
Yes, and that's how the volume and the architecture ties into this class. Is the data is in RAM. Well, we don't have any data used in this particular case, but we can see how we can use a load indirect, which is using the asterisk. Anything with an asterisk is indirect. Okay, this is a store indirect because we're storing the register value into a RAM location. And then we have a load immediate, which is this one here, because we are reading a location in memory into a register. Is that okay so far? You know, just kind of general idea. Does that mean that I can ask you guys to write an assembler for the toy processor as the next project? But you guys get the general idea, right? The general idea is we are representing a program not in binary code anymore, but in some way that is easier to read. Okay, that's the whole point. Is that okay? All right. So just to continue with this, okay, this instruction, as far as I'm concerned, is going to have a name of LD, but LD, I cannot use indirect I for indirect anymore. So we can just call this LDX from Y, and I'll use a parenthesis around Y just to mean that we are not moving from register Y into X. We are going to the location pointed to Y and put that content into X. But the syntax of the mnemonics is entirely up to whoever came up with the architecture to decide. Okay, so Intel has its own mnemonics, Motorola has its own mnemonics, ARM has its own mnemonics, and so on and so forth. So in the early days, there was no standardization whatsoever. So it becomes, well, I wouldn't call it very difficult, but when you change from one architecture to another architecture, you kind of have to relearn the syntax of the assembly language. They have some resemblance, but they are not necessarily exactly the same. Is that okay? Now, as far as the instructions that we are going to use in this class, there are two major representations. So when you look up i386 mnemonics or i386 assembly code, okay, there are two major formats. One format is called AT&T notation, and the other format is the Intel notation. So there are two different formats. The AT&T notation is what I am using in this class, and then the Intel notation is what you would use when you're using a Microsoft Windows platform. The assembler in that platform would use the Intel notation. Is that okay? They're just different notations. They're both used to represent exactly the same kind of opcode and the same kind of instructions, except they are just different ways of representing things. Is that okay? All right. So this is what we're using. We are using the AT&T notation in this case, and this looks like a interesting web page. Yep, this is actually a pretty good web page if you want to get a cross reference to the stuff that I'm going to talk about in this class. This is not a bad web page. Alrighty. So getting back to here. So the next thing we have to do is to look at the registers of the 386 processor, because it is a little bit convoluted. It's a little bit convoluted because the 386 is supposed to be a 32-bit processor. When we say something is a 32-bit processor, we are referring to the width of the ALU. Okay? If your ALU can add two 32-bit integers in one single operation, it is a 32-bit processor. If your processor can add two 64-bit numbers in one single operation, it's a 64-bit processor. If your processor can only add two 8-bit numbers in the ALU, it's an 8-bit processor. So that's typically how people define, what is it an 8-bit processor, a 16-bit processor, 32-bit processor, or these days, 64-bit processor? It has to do with the width of the ALU. Is that okay? So the 386 is supposed to be a 32-bit processor, but it's not a very pure 32-bit processor. Why not? What is the heritage of the 386 processor? This is historical, okay, but it is important nonetheless. So we look at the i386 processor architecture. What is prior to the i386 processor? What is its predecessor?
The I-286?
286, okay, 80 to 86, and prior to that is the 8186. There is such a thing, even though it was not used a lot. Okay? IBM PC only used the 286 and then moved on to the i386, but it did not use the 186 prior to the 286.
So the 186 was what, a prototype? Prototype for the 286?
It just did not make it into the PC, IBM PC computers. What about prior to that?
Isn't Tandy used?
I don't think Tandy used that either. And then prior to that is what? Okay, well, according to this scheme, it's probably something like this, right? But we don't like double zeros, so it's actually the 8086 processor. But that's not the processor inside the original IBM PC computers. The original IBM PC computers was actually using a 8088 computer or processor, which is a very close relative of the 8086, with the exception that the 8088 processor has an internal width of 16-bit, so the ALU can handle 16-bit by 16-bit addition, subtraction, and stuff like that. But the external data bus is only 8-bit wide. So it will take two data
Two clocks.
Well, it will take two memory operations, not two clocks. It would be more expensive than just two clocks. But it will take two memory operations to write the result of a 16-bit calculation.
So
and
you
they
can do
did
it.
that. Sorry?
So you can do it, it would just take longer.
It will take longer. It will be what we call bus bound, because your bus operation to the memory is going to be the limiting factor of how fast you can do operations for the most part with the 8088 processor. They did it because it's easier to route PCBs when you don't have that many wires going around throughout the entire board.
So is it because these are routed manually?
Sorry?
Were they routed by hand at this point or something?
Probably the routing technology was not very advanced, nor was the technology to make circuit boards. Because you have to remember, your auto router can say, oh, okay, I can easily get this routed using a 5-layer board. The question now is, can manufacture a 5-layer board within a reasonable amount of money? And back in those days, that was not really an option. You get 2-layer boards and maybe a 3-layer board at the most. So your auto router can say, yeah, I can do this. We can do a 32-bit data bus, but it will be too costly to make that motherboard. Okay. Now here is the funny part. Okay, the fun part is what is before this. It's the 8085 processor on one side, and has anyone heard of the Z80 processor? The Z80 processor, as a result, is a grand uncle of the i386 processor. So these are two kind of different family trees, but before this one, they both came from the same source. So the 8080 processor is the common ancestor of the 8085 and also the Z80 processor. I might be slightly wrong in the history a little bit. I'm never really good at history, but I think I got most of it right. Okay. So the Z80 processor is a remote relative of the current i7, i5 field processor, which is just further down the list a little bit, right? Because after the 386, what do we have? The 486, right? The 486, the 8486, and then we have the 586, but it's never called the 586 is called the Pentium, exactly. And then after the Pentium, they changed the name to Core. Yep, the Core, Core 2 Dual, the Core 2 thing. And then after that, it became the i357, approximately. And then with every single generation past the Pentium, I think they have an Atom variant to kind of low cost, single core version of the processors. All right. So, but why is this picture important? Well, this picture is important because what do you think is the ALU path of the 8080 processor?
Where does it go back to? Or
Like how wide is it?
How wide is the ALU? In other words,
8
when you
bits?
perform it. Exactly. Now, how did you guess that it's an 8-bit processor?
All 8s.
All the 8s, exactly. so who do you think is the ancestor of the 8080 processor?
A 4040?
Exactly. It really is. I'm not kidding. There is a 4040 processor. Look it up.
Processor?
I don't think so.
Well, 2 weeks would be much quicker.
You can't do much with it, but I mean, it could be.
Yep, there you go.
Oh my
Here's the
God.
4040 processor. Okay.
Wow, really?
Yeah. So this
Hey,
is
at least
the-
they're ones for the obvious,
Is that gold or?
if the i7 processor is a human, according to evolution, this may be a fish. Okay, so
60,000 instructions.
note tonight how I said, if evolution is true, okay? For those people
That's
who do
so
not believe in evolution, it's okay.
They got 12 bits
So-
in, 12 bits out.
It says this can do 60,000 instructions per second. How much can a new processor these days do?
What do you think?
lot.
Let's just do a quick estimate of how many operations we can do with a current i5 processor, a humble i5 processor. Okay, so a humble i5 processor runs at what clock frequency? That's
3.22.
okay. On the laptop, it's typically about 2-ish, 2.4, 2.4, 1.8, then thereabout, depending on whether you want to go for power saving or whether you want to go for performance. Okay, so let's just call it 2 gigahertz. Okay, so running at a clock rate of 2 gigahertz. Okay, the ALU these days can do 1 calculation per clock. If you can feed the ALUs fast enough, they can do 1 calculation per clock. So that means each ALU of each core can perform 2 billion calculations per second. Yep.
Now, I know at some point they started, because it was all about the clock speed before. Now it doesn't seem to be all about the clock speed
Because they cannot get the clock speed up any further.
Because it gets too hot.
It gets too hot for one thing, and then the second thing is they cannot get it up any further, because to get the clock speed up, you have to increase the voltage, and then to increase the voltage means that it's going to run hotter.
Yeah.
And because the transistors are getting smaller, they cannot handle the power dissipation when it runs
So how
hotter.
are they getting faster? Because I know probably 7, 8, maybe 9 or 10 years ago they were starting to hit 6, and then they actually scaled down, but somehow they're faster now.
Because they had these huge, ridiculously large heat sinks. It's like itty thin processor to heat sink. That's
Yeah.
that
So
big.
I used to
Like they were
have-
just dissipating more
I
and
used
more
to have
heat.
I
Then
think
they
it
just
was like a
started
Pentium
breaking
D,
down the
and it was
problem
like
into
4
multiple
gigahertz.
processors performing.
Yep,
one part of the
They
problem.
once hit 4 gigahertz. Okay,
and,
so
and my
I could probably
2.2
get mine on
gigahertz
4, but
supposedly goes faster.
Lock the
Mostly it's
voltage.
like underclocked.
Doesn't make a huge amount of sense to me.
okay, so when we're talking about just add and subtraction using registers, we are talking about 1 clock per instruction. Okay, so every single clock can perform 1 addition or 1 subtraction, and that's per ALU. Okay, per ALU. So now the question is, how many ALUs do we have, or integer ALUs do we have per core? Okay.
Per core, so each core has multiple ALUs.
Yes. Okay, so we can look up i5, okay, ALU per core, and I cannot remember the number. I know it is not just 1. Okay. So right here, this is even from just 2014. It says 3 general purpose ALUs per core.
Okay.
So if you have a dual core processor, you have 6 ALUs. Each one can perform 1 calculation per clock. So that means 2 billion calculations times 6.
12 billion calculations.
And this case
12
it would be
billion.
times 4, right? Because it's an i5. If we're using an i5, it would be times 4, right?
Depends on the variant of the i5, because the laptop variants only have two cores, or some of the variants only have 2 cores. And then same thing with the i7. i7 does not always they're not always quad core. Some of the quote unquote i7 processors only have 2 cores.
So where does threading come in?
Threading?
Yeah.
Well, threading is a operating system concept. It is not a low-level concept. It's an operating system concept. But hyper-threading is a optimization to help boost the performance of your throughput. It will boost the throughput of your computer system, but only by about 20 to 30%. So it makes you believe that there are twice as many cores, but that's really an illusion. So in reality, it only improves performance by 20 to 30%.
Still a lot.
Still a lot. So we are talking about, this is from 2014, which is more than 2 years ago. So according to Moore's law, things should be twice as dense today because 18 months has passed, right? So, but even using this underestimate of 2 gigahertz as a clock rate, 3 ALUs per core, 2 cores, and 1 clock per instruction, we are talking about being able to perform 12 billion operations per second. But that's bogus, okay? Because what do you do with the result of these calculations?
You gotta store them.
You got to store that, right? At some point, you have to go back to RAM and store all this stuff. And guess what is slow?
Right speed.
The write speed, exactly. So memory speed has always, I shouldn't say always, but has been the bottleneck of stuff, lately. Because you just cannot either get information to process or store the information that you have processed nearly as quickly as you can do all the processing.
Now, does bus speed become an issue before memory speed?
You cannot boost bus speed beyond a certain point. So if you look at DDR4, is that the latest technology for motherboards?
DDR6, I think.
DDR6?
They don't have it on the market, but I've heard of it.
Well, let's just take DDR4 as into consideration.
I
Okay.
remember when they had like 7210 or 3210, right? Stop that.
Well, what I'm looking for is the transfer rate. What I'm looking for is the clock rate of DDR, and okay, let me see. Right here.
2133 megahertz, which is tiny compared to the gigahertz speed the processor
Well,
is at.
2133 is 2.133 gigahertz.
Yeah.
So that's respectable. Okay. The module works at this particular speed and processes up to 17 gigabits of data per second processing. So with a 64-bit I/O and processing, it's expecting to be commercialized by 2015 and turned into standard by 2016. Is that reality now?
So this was written after April 2014, but before 2015.
Yep, go ahead.
It's also DDR4 that goes up to about 3,000 megahertz too.
Okay. But the 3,000 megahertz does not mean 3,000 transfers per second. In other words, we take multiple clocks per transfer. Now, how do we know that? Because it needs time, okay? The moment you select RAM and you say, this is the location, and this is the right operation, this is the data, it takes time in order for the RAM to update its internal content. And that's why you get all those numbers. When you buy RAM, you remember that you get at least 3 numbers, right? The CAS and so on and so forth. Those are the delays, okay? Those are the number of clocks of delays in order for RAM to update or in order for content to come out of the RAM module. So that means, even with a clock rate of 2 gigahertz, you're not getting even close to 2 billion transfers per second. You're looking at a fraction of that. So the memory is still a threshold. Well, it's still a restriction of how fast we can do processing because we cannot communicate with RAM as fast as we would like. Yep.
Is it possible to build a buffer area like right next to the processor itself to store that information and then have a second
It's called
processor?
caching, right? That's caching.
Would that speed up the process overall, or? is
Well,
there still a
cache
bottleneck?
does speed up the process a whole lot, and
If
that's
the
why
cache is full.
that's why the expensive processors have more cache than the less expensive processors. Because that's one determining factor of how fast you can do processing.
But depending on what you're processing, you might fill up cache still, and then you just slow down until it
Yep,
finishes.
yep, and then it becomes a problem of how do you structure your program so that you do not get into that problem. So every time you read something into cache, you use all the stuff that is cached before you reach out to memory again. the thing about, okay, this is also something that's relevant. When you use cache, okay, at least level 2 cache, okay, level 2 cache is not on a byte basis. So you're not caching just 1 byte. Whenever you're caching a chunk of memory. Which is also why DDR works, okay? Because DDR is not any faster than non-DDR technology when you're reading individual locations. When you say, I want location 16, and then I want location 275, and then I want location 1066, okay? If you do random access like that, DDR is not gonna help you. DDR helps a lot when you say, give me 512 bytes. Okay, when it goes into burst mode. Okay, when DDR goes into burst mode, that's when you get all the high-speed transfer. Because what it does is when you do the burst mode transfer, it will only latch out the data. It will only latch out the address once. Okay, and then it will say, this is the next location. 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 Without changing the address after that point. So now your processor, or the MMU, or the memory management processor, memory management unit of the processor, and the RAM, now they have to kind of synchronize. Okay, each one has to keep track of the clock and say, okay, this is another operation, this is another operation, this is another operation, this is another operation, with no actual electrical signal to do the synchronization.
So they're just counting clocks and hoping for the best?
They're counting not only just clock cycles. I think sometimes they can even do like between transitions of the clock.
They can tell if the clock's up and down.
Right. But that's where the speed comes in. But if you're not reading in burst mode, then you still have to send out the data, the address first, and then do the control line, wait a little bit, okay, and then do the write operation, wait a little bit. So you still have all the delay if you're doing individual memory location access.
I see. So instead of queuing each individual location, we're going to have to queue a bunch of them using one location.
Right. So burst mode is where DDR shines, and when you compare different type of DDR technology, some works better with burst mode, but they do not work as well for individual random locations. And then another the DDR technology will be vice versa. For individual random location, it's faster, but when you do it in burst mode, it is not as fast. So this is all kind of relevant because we are still looking at the x86 processor line. Okay, but getting back to this part here, okay, 32-bit, 16-bit, and 8-bit. So we look at the family tree, okay, and then we say this is when things were 4-bit, okay. This is the starting point when thing becomes 8-bit, okay. So the 8-bit processor starts here. By the time we get to the 186/286, I should say even here, it became 16-bit wide. By the time we get to the 386, it became 32-bit wide. Okay, and obviously once we get to, is it a core 2? Then we start to have a 64-bit instructions. Okay, so when we get to here, we have 64-bit instructions. Even though the ALU, I think with core 2, it's still 32-bit wide, the instructions will pretend to be 64-bit wide. Okay, but when you look at this heritage, and then you ask the question, how far can your i5 processor be backward compatible to in this entire family tree? Okay, where do you think it stops? Well, not all the way. I mean, it's not. It cannot go all the way back to 4-bit opcode compatible.
Pretty sure it stops at 32.
Right?
Why can't it go back to 4-bit? I mean, can't you just pad the instruction with hello zeros?
No, because the decoder does not decode beyond that point. So it does do all the stuff back to the 8-bit processor. Okay, so this is all the way back to the 8-bit one. So your registers basically are compatible to, at least instruction-wise, it is all the way compatible back to the 8088 or the 8086 processor. Why? In other words, starting from the 8086 or the 8088 processor, your current top of the line i5 or i7 processor can still execute instructions in 8088 mode. But why?
Because it's backwards compatible, right?
Because that's when Microsoft and IBM came up with PC-DOS or MS-DOS. So your new processor can run legacy code all the way back to MS-DOS 1.0. Okay? Which also means now we have a big problem, because now we cannot just say, oh, we got 64-bit registers, and let's just stick with 64-bit registers. Because you have to say, oh, but sometimes we want to look at those as 32-bit registers, or 16-bit registers, or even 8-bit registers. Okay? So now we have a kind of an interesting problem. So I will show you in a spreadsheet, this is the best way to show it, how the registers, or at least some of the registers, are allocated. So open a spreadsheet, there we go. All right, so we'll start with, okay, 1, 2, 3, 4. So this is a good place to start. So we'll start with, there are 4 registers that we use, kind of as general purpose registers. Okay, we'll start with register AL, okay, and each column is 8-bit wide. So column E is representing register AL, okay, that's the name of it, and it's only an 8-bit register. And then later on in time, we have a register called AH, okay, which is another 8-bit. But then you can look at both of these at the same time as AX. Okay, so AX is basically just looking at AH and AL together as a 16-bit register.
A high and A low.
Yep, exactly. Register A high, register A low. Those are 2 8-bit registers. AX is a 16-bit register.
Using the combination of what's inside those.
Using the concatenation of AH and AL. Okay, and then later on in time we have 32-bit registers. So as a 32-bit register, we are looking at 4 bytes, and it's called EAX. Is that okay? Okay, let me give you another view of this. Okay, we can also say that AX is the same thing as EAX, except we are only looking at the bits from 0 all the way up to 15. So bit 0 to bit 15 of EAX is also known as AX. Is that okay? It's just a window into the bigger register. Is that all right? Sort of? Okay. What about AL, L, and AHR? AL is the same thing as looking into EAX, but we're only looking at bit 0 to bit 7. And then AH is EAX, but only from bit 8 to bit 15. So EAX itself is a 32-bit register, but you can look into EAX and say, I don't need the whole thing, I just need 8 bits of it. Then you can say, which 8 bits do you want to refer to 0 to 7, or do you want to refer to 8 to 15? So you can use AL to refer to bit 0 to bit 7 of EAX. You can use AH to refer to bit 8 to bit 15 of EAX. Or sometimes you can say, but I need all 16 bits, okay? I need all least significant 16 bits of EAX. Then you can also call it AX. Okay? AX is referring to bit 0 to bit 15 of EAX. So there's this little kind of awkward thing about this particular processor because of its heritage, because of how it needs to be backward compatible. So it has all of these kind of different registers. So in addition to EAX, which is a 32-bit register, you have EBX, which is also a 32-bit register, ECX, and EDX. Okay.
These are all built into your processor?
Huh?
This is all built into a standard processor.
This is all built into
architecture.
the i386 and thereafter processors. Yeah.
So because of this, the backwards compatibility isn't really much of an issue? Because it's kind of like, if you don't
This
need-
is here because of the backward compatibility.
It's like simulating.
Oh, we
It's like
don't-
simulating the ability, like simulating a register that is only 8 bits wide instead of 16 bits wide, and like those segments basically.
so you only
Because
have.
it's giving you like a smaller window, it's just saying like.
Yeah, it's a smaller window into a wide register.
So physically, you have a 32-bit register, but you can look at different portions of that 32-bit register individually based on these other codes.
So
What's
essentially,
the
the
downside?
rest of the register's just wasted on an 8-bit program, or a 16-bit program.
Or no,
Yep.
you can probably, can you use different parts of that EAX register to store
Maybe the
different
waste
8-bit
space
parts?
for
Like you can have bits 16 to 31 be.
There's no way to refer to that individually.
Okay.
Yep.
So what's the downside? I mean, there is a downside, right?
The downside is your opcode gets complicated. Because instead of just being able to refer EAX, EVX, ECX, and EDX, now you need to have additional bytes called modifiers to
Maybe
say,
multiply by 30.
oh wait, I don't want the entire thing. I just need the least significant 8 bits. So it does complicate the opcode itself, so it makes a cisp even more complex. It's a cisp to begin with, and because of the layers of legacy code, now it becomes even more complex because, as a result of that.
And they have backwards compatibility because of drivers, or
Well, that's a good question. Why does the i386 processor has backward
Yeah.
compatibility all the way back? I think we might have touched on that a few times, maybe not in this class.
Because there's some of us who like to run old programs who would be really pissed if they didn't get to use it.
But you can run it in emulation. See, but the thing is, you can always emulate a processor with another processor. Now, it may not be fast enough, but you can still emulate it, right? But the driving force of backward compatibility is not Intel, it is actually Microsoft. Because they don't want to,
Redesign the way their operating system is.
right.
yeah, we went over
You
this.
can't emulate Windows.
Hmm?
You can't emulate the entire OS.
Yes, you can.
Well, I guess you can, but like,
Yeah.
it wouldn't work.
I didn't
for
like
us
Windows on a Mac.
If it wasn't
It was hell.
backwards compatible.
Well, I really do not know the real rationale anymore, because with modern compiler technology, cross compiling is not that big of a deal. How many people remember the PowerPC processor? Okay, some of you. The PowerPC processor is a joint venture of which two companies?
IBM.
IBM is one, and where's the other one? No, it's not Microsoft. Microsoft would never do something like that.
Apple.
It sounds like something Apple would do.
Apple, exactly. So the PowerPC is the joint venture between IBM and Apple. And one of the key feature of the PowerPC architecture is it can do emulation really well. In other words, it's a pretender. Okay, it can say, okay, do you want me to pretend to be the 68,000 processor, or do you want me to pretend to be 8086 processor? It can do it really well. Okay, it actually has hardware features in the processor to make it a very good emulation processor. And the reason is, IBM says, okay, I don't want to stay with the Intel processor line, okay, we want to use a new processor, but I want backward compatibility. So IBM says, I want to be able to emulate x86 instruction set so that I can still run MS-DOS or PC-DOS or whatever using this new architecture. Apple says, I don't want to use the Motorola 68,000 processor anymore, so I want this processor to be able to emulate the 68,000 processors. So that's why the PowerPC has this kind of weird feature that makes it very easy to emulate some other processors.
So why didn't they just go that route?
Take off. That
Yeah.
seemed like
Well, the
that'd be-
PowerPC did take off, okay? It took off in the case of Apple because there's an entire generation or generations of Macintosh that are powered by PowerPCs. And that's prior to OS 10. Okay, OS 9 ran on multiple platforms that were based on the PowerPC processor. IBM never released a PC, an IBM PC that used the PowerPC processor, but guess what their blades or their servers are running on? A PowerPC platform. And it even find its way into the PS3. The PlayStation 3 is also based on the PowerPC processor.
That's why I like supercomputers.
And you can, because each PS3 actually has 8 or 16 processors inside.
Yeah.
So you can network those things and make it a small little super server farm. Okay, now the other thing about these ABCD is they are not just letters that are sequential in the alphabet. A at one point in time actually stood for accumulator. B I think stood for base. C stands for counter, and D stands for data. So at some point in time, okay, in the heritage of the i386 processor, each one of these is actually a special purpose register. Only certain instructions can use the register A. Some other instructions can only use register B. Some instructions can only use register C, and some can only use register D.
Was that in order to save ROM space?
In order to save ROM space, correct. And also it reduces the use of the multiplexers and the multiplexers. Because you don't need to say, oh, I can refer to any one of these four instructions.
To do the same operation.
Yep, you hard code the register to the operation.
So that
like,
your mux would disappear and you would actually literally have one pin on your register bank for each individual data input,
Correct.
each individual select pen.
Yep.
Wow.
And say you just have to like implement something 16 times and something will repeat. Like,
Yep.
do, like, the
But those days were gone,
seconds.
okay?
Well, repetition, so you save a little bit of space, but.
Yep, but those days are gone, so now these are considered general purpose registers now. So you can use these quote unquote interchangeably. So each instruction can use any one of these registers.
So now it's really up the way we have it, kind of like in
Correct.
our
It is much closer to what we have in our toy processor now than what it used to
But
be.
the reason it's not a mux, is it? It's because they just have the space to write more instruction.
Because MUX takes transistors.
So
They
they don't have another mux. They just have more space to write more instruction. Is that why that? Is that
No,
why?
because by hardwiring certain operations to only certain registers, they can reduce the use of muxes and demuxes, and as a result, they can reduce the transistor count on the processor.
Just to save space.
Because back in the
But
past,
I'm
you can
thinking
only
that
fit
that's
so many
coming up for
registers.
Now, like the reason why now that we can is because we have more space.
Yes, we have more because the transistor density has increased considerably because it's doubling every 18 months. It's still going.
For now.
I think
They've
Hmm?
gotten to a point that they can
Intel
make
stopped
registers
that 'cause they couldn't keep up
the
with the
transistors
so
so
they
small.
They're even get to a point that they can't.
Right. They can put transistors on the side, 3D, stack it. Yep. Okay, so these are the so this is a little bit kind of awkward thing that we don't have to deal with.
Like biological.
So now we move on to the actual instructions. Okay, so this is actually kind of important stuff. Okay, so we are now actually moving on to real i386 instructions. So we are going to start with a move instruction, MOV. Don't ask me why they don't spell out move as in MOVE. Is that E really that significant?
Too much.
Yeah.
Just too much.
Just too much. But it's MOV, okay? So MOV is the instruction, MOV. And all of this stuff here is in one of these documents, okay? It's probably in this one and also in this one. Okay, so there are only several ones that I want to go through. As a CISC architecture, there are a wide variety of these instructions. So what I'll do next, for the next 10 minutes or so, is to use sample programs to help illustrate what these addressing modes are, okay? So I'll go to a temp folder and start to write some simple programs. So I'll say test1.lowercase s. So when you write assembly code in a Linux platform, using a lowercase s extension is quote unquote the standard. But Linux really doesn't care about extensions. Okay, so you can use any extension you want, but lowercase s is the standard for assembly source file.
Not that I'm not writing Linux, but what would it be if
I don't know because I have never tried the assembler in Windows. It's probably cross-compiled in Windows, but it's not something that I have tried. Okay, so we'll start to write a program. The first thing we do is to specify, well, this is not exactly needed. So I'll just write the program as is, and then as the assembler complains, I will explain what it is complaining about. Okay. Okay. And I'm going to turn off syntax highlighted because it's actually making it harder to read. So this is one simple program. Okay, EAX like that. So this instruction is basically copying the bit pattern 0 into register EAX.
So what's it going to do? Is it going to expand the bit pattern 0 to all 32 bits?
Yeah, so when you specify, you know, the value to put into EAX, you can specify it in any way that you can already in C or C++. So you can specify the value in base 10, in base 16, base 8. Same standard as in C. Yep.
It's the dollar sign.
The dollar sign signifies this is load immediate. Okay, so it is required. Okay, so the dollar sign is required in order to specify that this is copying the value 0 into EAX.
What's the percent sign?
The percent sign? The percent sign is also required. It signifies whatever follows is the name of a register.
Ah.
So those are the little things, little syntax things that we have to learn. Is the dollar sign is required in this case, and then the percent sign is also required in this case. Okay? But what really helps is this is comment, okay? It's the same thing as a // except it's a pound sign in assembly. So it's comments, okay? So after the pound sign, it's all comments, and the assembler does not really care what you type after this. So after this, you know, I'm just going to say this is really the same thing as EAX gets a value of 0. In other words, after this operation, the register EAX will be 32 zeros. Is that okay?
So what's the value before you define it? Is it random, just whatever was in there?
It's just uninitialized.
So if you haven't assigned something to EAX, the compiler will throw you an error. If you try to use EAX?
It won't give you an error. It would just, because, okay, if you think C let you do whatever you want as long as you convince the C compiler that you know what you're doing, this won't even ask. This won't even ask,
They just say,
do you
yeah,
really know what you're doing?
Trust you.
It just says, yeah, you're good.
Yeah. Yeah. As long as the syntax is good, it's good. Okay, it doesn't check anything at all. Okay. Now I want to equate this to the instructions that we have been working with. Okay. So in our instructions, this is really the same thing as a LDI, load immediate, register A with a 0. Or if you want to look at the actual opcode or the actual bit pattern, it is LDI, this one. So it's basically the 2 bytes 0, 110, 1100, and then followed by all zeros. Okay, 0, 110, 0, 0. Oops, I think I got it wrong here. 1100.
You wouldn't be able to do any backwards compatibility using our old codes because you've only got access to the extended registers, right?
I could do AL. I can say %AL.
Well, we can do %AL, but on the right-hand side, our codes.
In our code, because we only have an 8-bit processor, that's the only thing that we can do.
Okay,
So what I'm doing is trying to illustrate, what the instruction actually looks like. So the instruction, obviously, in this case, is going to be something other than 0, 110, 1100, okay? But what is happening is the constant that you want to copy into EAX is right after the opcode itself. Okay. Now we can take a look at that. Okay, so just let me finish this, and then we'll take a look at the actual instruction. Okay. So we'll stop here. Okay, so we'll just say right here, and then we'll undo. There we go. Okay, so now I'm going to run this through the assembler. So I say assemble -o test1.o test1.s. Okay, so this is the command to assemble a particular program written in assembly. The source file is specified as the last name. The -o means the output of the assembly, which is an object file, is named test1.o. Once again, the .o is really a convention. It is not required that you have to use .o as the extension of an object file.
So you could have to say .exe if you wanted, that would be fine.
You could.
Yeah, you can say .txt if you want to.
Well, exe would make more sense.
Now I'm going to use a program called object dump. Okay, so objdump, and I need to remember which disassemble all -d. Okay, so obj dump dump all is what -d -1.o. So this is doing the reverse. Okay, I'm looking at the actual binary code to reverse it back to what is the actual instruction. Okay, so let's take a look at the output of this.
This is kind of giving us the result of what the assembler did.
Right, this is the result of the assembly. Okay, So when you look at the result of the assembly of this one single instruction, okay, on the right-hand side you see the instruction itself, okay, because it's assembling it. It's looking at the actual code of the file and say, oh, that's the instruction that we're dealing with. But these 5 bytes, these 5 bytes are the actual locations corresponding to that one single instruction. But you can see how it resembles our LDI instruction, the 0, 1, 1, 0, 1, 1, 0, 0 opcode that we have with our point processor. Huh?
This is an hexadecimal. It's just in hexadecimal.
These are all in hexadecimal, correct. It's a different opcode, okay? B8 is 1011100000. But what you notice is the constant, the value that we're trying to copy into the register is right after the opcode itself. Just like our LDI instruction.
So the outcode's the B8?
No, that's the location in memory in which we're writing it. Or no, sorry, location in memory where the
Is that
instruction
opcode on
that
the
we're
ROM
calling
of this
is.
PC?
It is in the processor itself, yes.
The processor.
In the processor
So that
itself.
B8 is the location in the memory that the instruction that we're calling is located.
Location of ROM.
The location in
Location
ROM.
of ROM.
Well, how the Intel processor decodes the B8 is not, is not disclosed. I don't know for sure,
Oh.
okay? But the B8 is corresponding to our 011011000, which is the opcode. Now, each processor can have a different decoding. Okay, they can have a more optimized way of decoding and use up less ROM space or something else. Okay, but it does correspond to the action of our LDI instruction, which is the 011011000 instruction. The key part here is the 0 that we are specifying here is a part of the instruction. It is right after the opcode itself. Just like when we specify the LDI instruction, we also have to specify the constant right after the opcode. Yep.
So if you really know what you're doing, you can use this program to sort of reverse engineer something.
Oh yeah, you can definitely do it the hard way. The harder way. Yep.
Is that possible to do on programs compiled to an object file from something like C or C++? To look at what the
Yeah, absolutely. Object dump works on all executables, so you can actually disassemble any program you want.
You ever seen Call to Catch Fire? Show Call to Catch Fire? It's like basically a guy does this in the show. Like, but
So
it's-
can you find an executable on the PC and do an object dump on it?
You can find, I can do anything inside bin, right? So I can go to user bin, which is where most of the user programs are located. So there's a whole bunch of these, right? So we can just look at ls, okay? ls is no such file. Oh, ls is not there. Which ls? It's inside bin itself, okay? I don't know. Let's take a look at zip, okay? So we can do object dump -d of zip. Now, I will need to pipe it to less because otherwise it's going to be pretty long. So it will give you, the disassembled version of the zip program, and it has different sections. We are not going to talk about sections until a whole lot later. But yes, you can actually look at the underlying opcode of an executable using object dump.
Didn't we do something like this when we were
Use
practicing hacking?
Exactly.
Yeah, you
Right.
showed us this
Yes,
kind of.
I did something like that when I was hacking my own program.
All starting to make sense.
My own program gets it. Fine.
Yep.
What do you
Okay, so we got about 3 minutes left. Okay, so we got 3 minutes left. We can do one more code. Okay, we can do another test program. So this one is just copying from one register to another register. Okay, so it's copying from register EBX to EAX. No, it's copying from EAX to register EBX. So it's a copy. Move is a misnomer. Okay, you do not move bit patterns in a processor. You copy bit patterns.
Because there's no cut.
Because in the real world, you can move, right? Here's my dry marker. It was here originally, and I now move it over here.
That's a cut.
What happened to the other space that it was earlier?
It's still, the space is there, but it's deleted.
You got
Well,
zeroed
it's
out.
filled up with air, right? It's not with pen anymore. But when you do instructions like this, it's a copy. It's not actually moving because whatever it was in EAX is still there. You're just copying the bit pattern to override what is in B. So I'm going to go through the whole process real quick here. Okay, AS-O test2.O test2.S, and then we do object dump again with test2.O, and it produces the code of 89C3, which basically means the bit pattern 1000, 1001, 110, 0011 is representing this particular operation.
So it's a 2-bit or
It's a 2-byte opcode, right?
opcode.
It's a 2-byte opcode, as opposed to in our architecture, in our toy architecture, we have something that can copy like this. Okay, it's similar to what we have here,
Which is a 1-byte opcode.
which is a 1-byte opcode. Because in our case, we only have a very small number of instructions to implement, whereas the i386 has a pretty big number of instructions. So before we end today's lecture, I will just go ahead and look up the number of instructions for the i386 and see if we can find it.
Instruction listing.
Yep.
Yeah.
And just from the thumbnail, I think that gives you a pretty good idea of,
We'll be there a while.
yeah, exactly. It won't fit in 8 bits.
No.
How do you remember all of this?
Nobody does. That's why we have the assembler.
So Intel doesn't actually give you has never released the information on what's actually in their
proprietary, probably.
ROMs, the microcode instructions themselves.
They do not, but people have used various techniques. They file away the packaging of the processors, and then they use X-ray microscopes to actually look at the wiring and the actual transistors and stuff like that. They can reverse engineer a lot of stuff. It's interesting how people steal secrets from other companies.
You gotta watch the first 3 episodes.
I will look it up. How many seasons is it? 42. That's why I haven't watched it. But I usually watch shows as they start to